Assalamu alaikum guys. Today we are going to discuss about pressure and its measurement part 3, in which we are going to solve the different numerical problems and different cases where the implementation of the hydrostatic laws will be there, and you will see how the pressures are going to be measured by using different devices practically. So here we are going to start with the problem number 1. A diver descends from the surface of the sea to a depth of 30 meters. What would be the pressure under which the diver would be working above the dead surface, assuming that the density of the seawater is 1025 kg per meter cube and it remains constant throughout the system? So for that particular case, we need to be just start with the given data. Here it's just a hydrostatic, the use of the hydrostatic law is over here, in which when diver is going to be descend from the surface of the sea into the depth. This depth is from the datum. If the surface of the sea is going to be considered as a datum point, then the depth will be 30 meters down. So it will be considered as negative. So in the solution, we have an hydrostatic equation we have studied in the previous slides in our part 2, that is going to be represented in equation number 2.4. So by following this equation of the hydrostatic law, we can take the sea level as datum, considering z1 is equal to 0. Since z2 is lower than z1, that value, so it will be going to give you the difference equal to minus 30, z1 minus z2. So substituting these values and putting in the hydrostatic law and putting rho is equal to 1025 kg per meter cube, the increase in the pressure P2 minus P1 can be calculated by using this equation. So it will be P2 is the surface level, so it will be 0, but P1 is going to give you the point where the diver is there within the water. So it will be minus 1025 into 9.81, that is rho GH. Actually the formula that we are going to be using over here, it is rho GH. So if P2 minus P1 it will be equal to 0. Why? Because P2 is considered at 0. It is at the datum point. So for P1 it will be rho into G into H. So for this particular case, your rho density is 1025, that is given in the statement numerical problem, and 9.81 is the G value, and the H value is Z2 minus Z1. It is minus 30 minus 0. 0 is considering the datum point at the sea level, surface of the sea level. So it is going to give you the answer in Newton per meter square, that is 301.7 into 10 is to. Here we start with the problem number 2. The pressure intensity at a point in a fluid is given as 3.924 Newton per centimeter square. Here the pressure intensity is given. You need to find the height of the fluid when the fluid is number 1 water and number 2 oil with specific gravity 0.9. So it's very, you can say, easiest form of the problem statement, in which either way you need to be determined. In the first problem, the height, mean pressure heads were given, and you need to determine the pressure intensity. Now in this problem number 2, the pressure intensity is given for at any point within a fluid, that is given data, and you need to find out the height of the fluid, mean the heads of the fluids. So here for the water and for oil of specific gravity 0.9. So one by one we can use the hydrostatic law with the pressure intensity given 3.924 Newton per centimeter square. So in SI system it will be 3.924 into 10 raised to power 4 Newton per meter square. So first you need to be consistent with the units, that will be SI system. And now you can use the Z, mean P is equal to rho GH is the hydrostatic law, and taking your pressure head on one side, you will be having this law in the form of pressure intensity P over rho into G. So you are getting rho into G in denominator and P in numerator. So in this way, the Z is going to be represent H, mean the pressure heads. So this pressure head for water, if the formula is going to be established once, then only the inputting of the values be there for corresponding type of the fluid. So for the water, the first one, the density is 1000 kg per meter cube and G is 9.81 and pressure intensity is a given data. So the same pressure intensity you are going to be inputting in numerator, and rho into G you are inputting in denominator, and you are getting the answer. It is 4 meter of the water. And the second point, for the oil specific gravity. So for the oil, you need to be first of all determine the density. This density will be the specific gravity multiplied by the density of the water. So you are familiar with that. So 0.9 into 1000, it will be 900 kg per meter cube. Specific gravity, or sorry, density of the oil. So for after getting this density, it will be very easier to input in the hydrostatic law for the pressure heads. So it will be P, pressure intensity same, that is given in the given data. Rho naught is the density of the oil into G, that is 9.81. So you are inputting all of the values, and again you are getting the answer, 4.44 meters of the oil. So in this way, from problem number 1 and problem number 2, we have concluded that once in for any system, if the pressure heads are given, then how the pressure intensity can be determined, and if the pressure intensity is given, then how the heads can be correspondingly height of the fluids or pressure heads, how it can be determined by using the hydrostatic laws. Now problem number 3. An open tank contains water up to a depth of 2 meters, and above it an oil of specific gravity 0.9 for a depth of 1 meter. Find the pressure intensity at the interface of the two liquids at the bottom of the tank. So here we have a case, and the next slide we will see. On the right hand side you can see this figure 2.4. This is the system actually that is given in this problem statement, in which first of all in one tank two type of the liquids have been put. One is oil and second one is water. So if you are going to be say your water as B and your oil is at A, so the height of the liquid of oil within the tank, it is 1 meter, and for the water it is 2 meters. So if we are going to be enlist the given data, so it will be comprises of the height of the water, that is Z1 is equal to 2 meter, and height of the oil as Z2, that is 1 meter. Specific gravity of the oil is 0.9, density of the water is 1000, and if the once density of the water is given, then the specific density of any other liquid can be determined by multiplying it with the specific gravity. So here specific gravity is given, so the density of the second fluid, mean the for the oil, can also be determined. It will be 900 kg per meter cube. Now pressure intensity at any point now is given by, you are familiar with again the same hydrostatic law with there. For this purpose also, the pressure intensity is equal to rho G H or rho G Z. Okay, so Z is the pressure heads. So you can see over here for different type of the fluids. So now we have the different points at which we want to determine the pressure heads. So mean pressure intensity. So first of all, the pressure intensity is required to determine at interface of two liquids, oil and water. So it may be you can represent at point A anywhere at this surface, this contact surface of oil and the water. So any point you can denote as A at this surface, and at here the pressure will remain the same. Okay, why? Because the height of the column, mean height of the pressure head of the oil, is same throughout this thickness of the or width of the tank. So if this height will remain same, there is no variation for this pressure head, then pressure intensity will remain same. Your pressure intensity is directly proportional to pressure heads. So at each point on this interface of oil and water, these two liquids, the pressure intensity will remain same, and we can determine it very easily. We have rho 2 into G into 1. So rho 2 is the density of the oil, this above liquid, multiplied by 9.81 into 1. That 1 is simply the pressure head H, the Z value or H value. So you are going to be inputting over here and you are getting the answer in Newton per centimeter square. Now, at the bottom of the tank, the second point at which the pressure intensity is needed or required to be determined is at the bottom of the tank. So, for the bottom of the tank, you need to determine the pressures. So, whatever the pressure you are calculating for the oil, you are adding the pressure head, the mean pressure intensity due to the pressure head of the second liquid below the oil has been kept in the tank, that is water. So for this water, the height of the liquid is 2 meters, mean the pressure head is 2 meter. So equal to this intensity, the pressure has been generated at the bottom, and the sum of the pressures at the bottom will be the pressure generated due to the water column plus due to the oil column, oil liquid column. So here at the bottom, your total intensity will be rho 2 into gz2, mean the hydrostatic pressure due to the oil, and the second part you are adding the hydrostatic pressure due to the water. Okay, both of these liquids, so you are adding at the bottom. So the first you have determined earlier. Okay, so you are just inputting the values, and for the second you are inputting the correspondingly pressure heads and the density that is for the water. Okay, so correspondingly you are getting the answer. That will be, the first will be 8829, that will be the same you have determined for the oil, and the second one is the additional part, additional pressure, that will be due to this water below the oil surface. So it will be 28449 Newton per meter square, and Newton per centimeter square it will be 2.8449. Now problem number 4. The diameters of a small piston and a large piston of a hydraulic jack are 3 centimeter and 10 centimeter respectively. A force of 80 Newton is applied on the small piston. Find the load lifted by the large piston when number 1. The pistons are at the same level. Small piston is 40 centimeter above the large piston. Density of the liquid in the jack is given as 1000 kg per meter cube. Okay, so see how this system is going to be work. Previously, when smaller piston and larger piston were at the same level, then it was 888.96. So what does it mean? That your height difference or level difference will going to cause an increase in efficiency of this piston system. This system has been going to give you more efficient results once the level of the piston has been kept higher than the for the smaller piston kept higher than the larger piston. So it is going to give you the more answer, mean the more weight can be lifted by the larger piston. So it is mean to say that height of this liquid, mean due to the hydrostatic pressures are responsible to lift more weight from the larger piston. Now, problem number 5. A cylinder contains a fluid at a gauge pressure of 350 kN per meter square. Express this pressure in terms of a head of water having a density and head of the mercury with density, relative density 13.6. What would be the absolute pressure in the cylinder if the atmospheric pressure is 101.3 kilonewtons per meter square? So this is very simple, again like your first problem or second problem, in which the pressure and density is given and you need to determine the pressure head for water and the mercury. So this needed to be solved you by yourself. Your solution is given over here, 35.67 meters of water and 2.62 meters of the mercury. The head you need to determine. Okay, so in the pressure intensity keeping the same, you need to use the same hydrostatic law and you can determine the heads for the water and for the mercury. Now we are going to solve the problem number 6. What is the maximum gauge pressure of the water that can be measured by means of a piezometric tube 2 meter high? Mass density of the water is same, like 10 is to power 3 kg per meter cube. So if this is the particular case, again following the same hydrostatic law, your pressure will be equal to rho g into h. So here the reverse case be there than the problem number 5. Here you need to determine the pressure head is given, that is 2 meter height of the piezometric fluid within the tube. The pressure head is given and the density is given and g is given. You need to determine the pressure. So pressure can directly be measured by following the hydrostatic law and you can find it very easily. Now from the problem number 7 onward, we are going to solve the systems of the different type of the manometers. The first problem, problem number 7, is in which a U-tube manometer similar to that shown in the figure is used to measure the gauge pressure of a fluid P of density rho is equal to 800 kg per meter cube. Density of that particular fluid is given to you, that has been kept or that is in the manometer, and for which it is required to determine the density. If the density of the liquid Q, so what was the liquid Q in the theoretical part 2 we have discussed in detail, and also in the figure this liquid Q has been given. This liquid Q is actually the manometric fluid that has been shown by the hatched line in this figure, this U-tube. So this is the manometric fluid. So it is having a density 13.6 into 10 raised to power 3 kg per meter cube. Density is given for the manometric fluid. Okay, so density is given for the fluid for which the pressure intensity is required to determine. What will be the gauge pressure at point A? So you need to determine the pressure at point A actually, but for two different cases. The first case is in which H1 is equal to 0.5 meter and D is 0.9 meter above the BC. Okay, so here you have this 9 BC, where the first, you can say, in the left limb the manometric fluid level is there. So you are going to be cutting cross section through this point, this level, and then it is going through the other part or other limb, right limb of the manometric tube. So here you're going to be having this BC cross section. So above the point B, this H1 is the height, is given 0.5 meter, and it is given in the case 1 when your D point is above the BC. Okay, so here anywhere the point D is there, so giving you in the height of the manometric fluid in the right limb at equal to H2. The second case is there where H1 is equal to 0.1 meter and D is 0.2 meter below the BC. Okay, so your point D will come down, so it means the negative pressure should be developed. So your H1 is very small. Okay, so this B point will become up. Okay, if first case H1 is equal to 0.1, so for 0.5 meters, so second case H1 is 0.1, mean very small value. So your B point will rise up here and your D point will be lower than the point C. Okay, this cross section BC. So in this particular case it's obvious. The first case will give you the positive pressures, mean gauge pressures, and your second condition will give you the vacuum or negative pressure. So see how it happens. For the A part, you have the manometric density of the manometric fluid given in the statement, problem statement. Your density for the fluid for which the pressure intensity is needed to determine is also given in the problem statement. H1 is given and H2 is given, and it is positive. That is above the cross section, this BC. Okay, so you need to be use the same equation at point A. If the pressure at point A is needed to be determined, then it will be equal to this height, this pressure intensity due to this height of the liquid from point A to point B, and minus this height of the fluid, that is manometric fluid, from point C to D. So 13.6 into 10 raised to power 3 into 9.81 into 0.9, it is the height of the pressure intensity due to the manometric fluid, and you are subtracting it from the pressure intensity of the fluid for which it is filled within the vessel, so in the manometer. So it will be 0.8 into 10 raised to power 3 into 10 raised to 9.81 into 0.5. Okay, so 0.5 is the H1. So H1 value you need to be input over here, and H2 you need to be input for the manometric fluid. So if you are subtracting both, you are coming at point A. Okay, so coming starting from here, So this pressure intensity coming up minus this pressure intensity, and you will be here at point A. So again, I am repeating this. In part 2, I have explained you that why we are not considering this part from B to C, this 180-degree bend, the pressure intensity due to the manometric fluid present in this bend we are not considering, because the pressure exerted by the right hand side of the bend is going to be cancelled out due to the pressure caused by the manometric fluid in the left hand side of this bend. So these are going to be cancelled out. Okay, this pressure intensity is equal and opposite, and this is going to be cancelled. But here is not the case. Here the direction is downward. Okay, this is going to be causing pressure in the downward direction, and here it is going to be causing in the upward direction. It is a in this particular case. So if this is the case, then you are going to be having this sign convention, and finally you are having the answer 116.15 into 10 raised to power 3 Newton per meter square. Putting your h1 is equal to 0.1 meter and h2 is equal to minus 0.2 meters, okay, since d is below the bc. Second case is going to give you the d that is below the point c. If this is the particular case, then you are getting your h value in minus. So minus 0.2 you need to be input over here. Rest will remain the same, and you are getting your answer in negative. This negative is going to show you that obviously it will be below the atmospheric pressure, and you're getting a vacuum, I mean negative pressure for this particular fluid filled here over here. Now your problem number 8. A U-tube manometer is arranged as shown to measure the pressure difference between 2 points A and B in a pipeline conveying water of density rho equal to 10 raised to power 3 kg per meter cube. The density of the manometric fluid Q is 13.6 into 10 raised to power 3 kg per meter cube. A point B is 0.3 meter higher than the point A. You need to calculate the pressure difference when H is equal to 0.7 meter. So this derivation we have also done in our part 2, where this particular type of the case be there once the fluid is flowing within a vessel, within a tube. So we are going to be connecting a U-tube manometer between these 2 points within this particular vessel or tube. Okay, so this is going to show you a system where water is flowing in a pipeline system that is conveying the water from one point to other point. So it may be a water supply system, it may be a sewerage system. Okay, so one point within this pipeline system is point A, and second point is point B, and this point and point B is further connecting with the help of these tubes through towards the U-tube manometer. Okay, so the manometric fluid has been filled within this, and CD is the cross section where the first again the first level of the manometer has been going to be considered, and the H1 is the height of the manometer fluid. A is the height from the cross section CD till the point A, and B is the height from the cross section CD, mean the datum point, till point B, and this difference of A and B is equal to 0.3 meters. Okay, so then you need to be calculate the pressure difference when H is equal to 0.7 meter. H is also given, that is 0.7 meter. The difference between B and A is also given. Okay, and the manometric fluid, the densities are also given. So what you need to determine, you need to determine PB minus PA. So if this pressure difference PA minus PB is needed to be determined, for that you need to first of all enlist the given data B minus A directly. You have this equation of the pressure difference directly from the part B. So you can refer the part B of our chapter, this video session, and then what you can do, you can just use the same equation as it is. Okay, so here B minus A is equal to 0.3, that is directly given, and you can input over here in this equation, and you are having the other part of it, and finally you can get the answer. Now problem number 9, for this going to be represent this particular system, and for this particular system again the equation has been derived and given in our part 2. You have an inverted U-tube of the form shown as used to measure the pressure difference between 2 points A and B. Again the pressure difference is required to be determined from point A till point B, Where the point A and B are not at the same level, they are going to give you some differentiation between both of the levels. Your point A is from this above surface, the contact surface, this point is A distance, and from here till cross section XX it is H, and again on the other side for the point B it is B. So here the 2 points A and B is in an inclined pipeline through which the water is flowing. Again, the density of the water is given. The difference of the level H is equal to 0.3 meter. A is given 0.25. B is given 0.15. Calculate the pressure difference PB minus PA if the top of the manometer is filled with the air and second oil of the relative density. Now the equation will remain same, and you can take a reference of from the equation that will be going to be used for this type of the differential manometer, inverted U-tube manometer. So for this inverted U-tube differential manometer, the equations are given. What you need to do, just you need to be considered in first case the air has been filled in this U-tube manometer, and secondly the oil of the relative density 0.8 has been used as in manometric fluid. So in either cases the pressure at XX will be same in both of the limbs, so that XX, so we are having a cross section, so in here it will be the same, but on the other side we need to be determined. So your PA minus PGA minus rho manometric, and on the left hand side it will be right hand side it will be PB minus rho G B plus H. So these equations are the same, those are taken from part B. So PB minus PA will be this equation. Okay, so if the top is filled with the air, so manometric fluid, the density will be negligible compared with the density of the fluid for which it is required to determine the pressure. So the manometric fluid will give you almost negligible intensity. Why? Because it is air. So for the air, for the gas, we are going to be considering as negligible. So therefore you are neglecting that part, and finally you are getting or inputting the corresponding values for B, for A, for H, and for the rho of the water, and you are getting the answer equal to 1.962 into 10 raised to power 3 Newton per meter square, neglecting the density of the manometric fluid. But if the manometric fluid is in the second case, B case, oil of relative density 0.8, then you need to multiply the density of the water with the specific this relative density 0.8, and then you have to use this equation. The same equation can be used, but by using the rho manometric, you get the density of the manometric fluid by multiplying it with 0.8, and then you will get the answer. That will be minus 392.4 Newton per meter square. Now the problem number 10 is going to give you a very simple example of a U-tube manometer containing mercury is connected to a pipe in which a fluid of specific gravity 0.8 and having a vacuum pressure is flowing. The other end of the manometer is open to the atmosphere. Find the vacuum pressure in the pipe if the difference of the mercury level in the two limbs is 40 centimeter and height of the fluid in the left from the center of the pipe is 15 centimeter below. So you can see this kind of the U-tube manometer in which the vacuum, the negative pressures has been generated. So this manometric fluid having a density that is given with the having containing a fluid having specific gravity equal to 0.8. So density you need to determine by multiplying it with the density of the water. And for this particular fluid for which the negative pressures are needed to be determined, for that particular case the value is given, that is 800. Okay, density is given. So you need to be first of all having your specific gravity is given, that is mercury. The manometric fluid is containing mercury. Okay, so this fluid is mercury, this manometric fluid. So for the mercury, this relative density is 13.6. So you can determine the density of the mercury by multiplying the relative density of the mercury with the density of the water. So 13.6 multiplied by 1000. And for the density of first density of the fluid, you have the relative density 0.8. So you can multiply 0.8 with the 1000 and you will get 800. So in this way you can determine the density of both of the fluids. So for this particular fluid the density will be 800, and for the mercury it will be this value 13.6 into 1000. Okay, so Now the second case is the heights are given. The manometric fluid will give you the 40 centimeter, and the above in the left limb, this height for the liquid for which the pressure needed to be determined, negative pressure, it will be 15 centimeter. Okay, so now the difference of the mercury level H2 is equal to 40 centimeter, and it is 0.4 meter. Height of the liquid in the left limb H1 is equal to 0.15. Both values are given. Let the pressure in the pipe is equal to P. Equating the pressure above the datum line AA is, then we get, so again we are going to marking a section where we have a vacuum pressure, mean the surface or the upper surface of the manometric fluid, and then it is going to be connecting on the other side in a similar way, giving you the equal and opposite pressure in the this particular band, 180-degree band. Now, what is the case on the right limb? Here, at the right limb, the manometric fluid is going to be directly have a contact with the atmosphere. So here you are getting the atmospheric pressure, okay, in the right limb. So if this is the particular case, then how you can determine the pressure? This pressure can be determined, the pressure at a point within this vessel plus the pressure due to this fluid within the left side limb, and plus the pressure head caused by this manometric fluid. Okay, so in this way the P can be determined. On the other side of, on right hand side, this is the system that is from the left hand side. Left hand side you have the pressure, okay, created, the vacuum pressure, negative pressure created at the center of this vessel, plus the pressure due to this fluid within this manometer above the manometric fluid, and then the pressure caused by the fluid, that is the manometric fluid, equal to 40 centimeter pressure head. On the right hand side, if we are going to be equate right and left hand side, so equal to that on right hand side there is only the atmospheric pressure, and that atmospheric pressure is going to be considered as a datum, so it will be 0. So P is equal to will be left with this negative values. So you are going to be just inputting the values for the manometric fluid and the fluid for which the pressure is needed to be determined. So finally you are getting the negative answer. So the vacuum has been created, mean the negative pressure is going to be caused by the fluid putting in the, or has been kept in the manometric fluid, for which we are interested to determine the pressure. It will be negative pressure. Now problem number 11, a U-tube manometer is used to measure the pressure of the water in a pipeline which is in excess of the atmospheric pressure. The right limb of the manometer contains mercury and is open to the atmosphere. The contact between the water and the mercury is in the left limb. Determine the pressure of the water in the main line if the pressure in the level of the mercury in the limbs of the U-tube is 10 centimeter and the free surface of the mercury is in level with the center of the pipe. If the pressure of the water in the pipeline is reduced to 9810 Newton per meter square, calculate the new difference in the level of the mercury. Sketch the arrangement in both of the cases. This problem statement seems to be complex, but it is very simpler if we go towards the solution. Here what is the case? You have a simple U-tube manometer. Okay. In this U-tube manometer, the fluid has been kept for which the pressure is needed to be determined, and the manometric fluid has been filled. If you see this figure 2.11a, so here you can see the manometer fluid, that is most of the cases it's mercury, and at point D it having contact with the atmosphere, so atmospheric pressure has been generated at point D. So this point B is at the top surface of the manometric fluid in the left side limb, and you are cutting a section over here. Okay, and due to this height of the fluid, this column, this pressure head, this is going to be causing a certain pressure on the mercury. It is pushing down and it is coming up. Okay, so right limb, left limb, the water has been kept in this manometer, and the mercury is filled as in manometric fluid. All of the system is same. Okay, it is not going to give any difference. But what is the second case that is going to give you a certain, going to be involve a certain calculations? Those are going to give you a case when whatever the pressure you are calculating for the first system, you need to reduce this pressure to 9810 Newton per meter square. Okay, so for this particular case, you need to calculate the new difference in the level of the mercury. Now, see this figure. Here in this figure, if this B and C is the level for the first case, from the first case, we are now reducing the pressure. What does it means? Reducing pressure means that the negative pressure has been created. Mean the level of the mercury in the left side limb needed to be increased. The pressure has been released or reduced by this liquid. If pressure is increased, then this mercury level should go down. If pressure is decreased or reduced, then this mercury level in the left limb should be go up, should be risen up. So in this particular case, we are reducing. Here you can see the second part of this statement. The pressure of the water in the pipeline is reduced to 9810. If reduction will be there, it will be the vacuum, it will be negative pressure. So this negative pressure will cause the rising of the manometric fluid in the left limb. So from B to B dash. Now on the other side, your C point is also been going to be your if it will go up, then your point D will go down. So if in the right hand side your point D will go down, it will be D dash, and of course your C point will also be go down. It will be same if you are going to be cut an aligned cross section, so it will be C dash. Okay, so finally which point has been actually going to be displaced? It is B and D. Okay, so your B point will be now at B dash or B steric, and then your D has been going to be come down as D dash. So in the left limb it will be go up, and on the right limb it will be go down. Okay, from D to D dash and from B to B dash. So if we are going to be represent this difference of the level with x distance, this is needed to be determined. Okay, so and this difference of the new difference of the level of the mercury. Now the difference of the level of the mercury is from the new level of the B and the raised one B and the lowered one D. Okay, so this difference 10 minus 2x needed to be determined. If 10 is the distance from B to point A, then it has been risen up the B from B to B dash equal to x distance. So this same x distance will be from C to C dash, and from equal to x distance your D has been come down in the right side limb of the manometer equal to x distance. So from x of the top and x from the bottom on right hand side, this difference new level of C dash and D dash, this difference will be 10 minus 2x. So this 10 minus 2x is actually the now new difference between the mercury levels, okay, on right and left hand side. So for this system, where from the actual system we are reducing the pressure within the pipeline, creating a vacuum, we need to be determine the new pressure head, new level difference level between the mercury or the manometric fluid. So starting with the solution, the first part is very simple. You can solve it by yourself. Here you can see again the same system, okay, in which the point B and C will there. The difference is 10 centimeter pressure head, and you need to determine the pressure at point A. So for the pressure at point A, you need to be going to be got a cross section. So on the right hand side, on the left hand side, you are equating both, and finally you are getting your answer for PA. So this you can solve by yourself. We will focus on the second part that we have discussed. So the system I have explained you earlier. Okay, so what you need to determine this 10 minus 2x. The same equation you are going to be used, but with the difference of the pressure heads now. Your heads are going to be changed in this case. Okay, so if you now want to cut another section, a new section B dash and C dash, and you need to write the equations at B dash and C dash, it will be in terms of x. Your x will be unknown. So the equation will be the same, the values will be the same, but only the pressure heads now will be unknown in terms of x. Your x is unknown. So you are going to be determine the x at first step, and then the 10 minus 2x will be the difference between the mercury in both of the limbs, right and left limbs. So this 10 minus 2x, you can input the x value and you can determine this difference. It will be 8.016. So rest of the equations will same and the solution will same. Now problem number 12. You can see a conical vessel having its outlet at A to which a U-tube manometer is connected. The reading of the manometer given in the figure shown when vessel is empty. Again, two cases be there. Find the reading of the manometer when the vessel is completely filled. You can see the system over here. You have again a U-tube manometer filled with a manometric fluid in which another tube has been connected with another fluid for which the pressures are needed to be determined. Now there is another modification for this particular problem statement in which a conical vessel has been attached at the top of this tube that having a certain dimensions like this. So if this vessel, you have two cases you need to be determined, in which first case when no fluid has been, your conical vessel is empty, it is not going to be filled with the fluid is running or flowing only within the tube of the manometer. And the second case is when your vessel, conical vessel, is filled with the fluid with the water. If this is the particular case, then how the situation going to be changed? This is reverse of your problem number 11, as I have told you. Okay, in that particular case the negative pressure has been created, but here the gauge pressure has been created, mean the pressure will be increased. Now due to the increased pressure of due to this conical height, okay, this pressure head within the conical vessel, it contains certain height, and equal to that particular height the pressure heads are going to be generated. Those pressure heads are going to create an additional pressure intensity, and equal to that pressure intensity the more pressure has been inserted in the tube, the manometer, and your manometric fluid will be go down in the right limb, and with the equal height it is go up in the left limb. So in this way you need to be determine again the difference between the mercury levels, okay, in both of the tubes. So the same, you can say, concept will be there, but only the difference is here you need to be increase the pressure due to the fluid present in the manometer. So in the first case you have correspondingly heights with you. You have this cross section xx, okay, and you have the corresponding densities with you. You can determine the pressure and this head of the water, that will be equal to 2.72 meters. Okay, this h1 can be determined very easily. So if your vessel is full of water, then an additional pressure due to this vessel you need to be consider, and you need to be determine the y actually. So once the y value, okay, so I mean this difference from the initial level xx to zz, okay, so it will go down. So from xx cross section your manometer is now going to be pushed down, and its new level will be z, and from here you are going to be cut again another cross section, that will be zz, and this y will be the difference in the right hand side limb, and both of the difference is going to be, one is go up and one is go down. For both it will be total head plus 2y, okay. So due to this difference, the difference of the mercury level in both of the limbs will be there. So here in this particular case, first of all again the y needed to be determined, and then 20 plus 2y will be the difference between the mercury level, mean it will be the reading of the manometer or the pressure head caused by the fluid within this manometer. Last problem is problem number 13. It is going to be give you with the help of a figure that is containing two pipes having the same fluid of density 990 kg per meter cube are connecting using a U-tube manometer. What is the pressure between the two pipes, if the pressure difference between the two pipes, if the manometer contains fluid of relative density of 13.6. So this is manometric fluid, okay. So that having a certain density 13.6 into 1000, so containing a certain heights, pressure heads, those are given from point A also, from point B also, and the difference of the manometric fluid with from right to left limb is also given. So what you need to determine, you need to determine the pressure difference PA minus PP, okay. This now you can solve it by yourself, solve it, and we will discuss it in our online sessions. Thank you so much for this part number 3, guys. Now we are going to be start our hydrostatic pressures for the submerged bodies. Our next part will be going to be comprises of that. So try to solve these numerical problems at home, and we will discuss in online session. Thank you so much.